we looked at finding a basis for the row and column of a matrix, the row space and column space of a matrix. And then we defined the null space of a matrix. And by doing the elementary row operations to a reduced row echelon form, we can then identify all those little components of, not little components, but we can find the basis for the row and the column and all that stuff. So I wanted to do that again just as a quick exercise. And we'll use this matrix. It's a 3 by 3. Actually, I wanted a non-square matrix. Let me see if I can find a non-square matrix. Take a look at number 19, maybe. So this is a 3 by 4 matrix. Let's take a look at 3 by 4 matrix and try to find a basis for the row space, the column space, and the null space. And then let's see where we can go from there. So our idea again is to row reduce. And it looks like it's almost in row echelon form, except we'll do one more step to get rid of this one down here. So we'll take the second row, multiply that by -1, and add it to the third row. The first row stays the same. Second row stays the same. And then the third row becomes 0, this is 0, this is 0, and then this is -2. So we're kind of done, I suppose. This is in row echelon form, but if we go all the way to reduced row echelon form, then we can see what else happens. So I'll do a couple of steps here. I'll get rid of this number here, and I'll change this into a 1 in 2 steps. So I'll take row 2, I'll multiply that by -1, and I'll add that to row 1. So row 2 doesn't change. I'll start off by writing that. Now, row 1 will be 1, and this will be a 0. And then -1 times -1 is +1 added to 0, -1, and -1, so that's 0. And at the same time, I'll multiply this by -1/2, multiply row 3 by -1/2, and replace row 3 by that, so that I just have 0, 0, 0, 1. So again, it could be done, but I'll take out this last bit over here. I'll just make this into a 0. So row 3 multiplied by -1 added to row 2. Because I want it to be reduced row echelon form, I need to have 1s wherever there's a non-pivot row, or whenever I have a leading variable, and everything else above and below that should be 0. That makes it a reduced row echelon form. If I had it here, this is a regular row echelon form. That's good for most things, but if we want a reduced row echelon form, I want to wipe out all those other things that are that have a 1 in the leading coefficient. Everything in that column should be 0s. So, yeah. It's okay to switch rows for those things, yeah. Okay, what was I doing? I was adding row 3, multiplying that by -1 and add it to row 2. And then that just gives me my 1, 0, 1, 0, 0, 1, minus 1, 1, 0, 0, 0, 1. Oh, yeah, which is the whole point, right? Okay, so I have my reduced row echelon form of matrix. Now, to find the basis for my row space, I have to look for all the non-zero row vectors in R containing a leading coefficient of 1, the leading 1 in each of these things. And that forms a basis for the row. By the way, let's make a couple more observations about A. A is a what by what matrix? 3 by 4 matrix. So in terms of a M by N matrix, your M is 3, your N is 4. So our row space is where? What is the dimension of the rows? If I take a look at the rows and imagine the rows as vectors, how many dimensions is that? We're in R4 is what I was trying to say. It's each of these things is a 4 vector. Okay? But how many rows do I have? How many non-zero rows do I have? I have 3 non-zero rows. So my row space can be the span of 3 vectors in R4. So the 3 vectors in R4 are going to be just all the non-zero rows that I have. So 1, 0, 1, 0, 0, 1, minus 1, 0, 0, 0, 0, 1. For me, it doesn't really matter. I think the book likes to see things in column vectors. They want to see vectors as columns.
But we don't have to, right?
No, I wouldn't care about it. Unless you have to write it as a column vector.
Well, yeah, but like,
yeah, but there are cases where you need to, we say that this vector is applied to a matrix, in which case you have to put it as a column vector. Okay, so the span of 3 vectors in R4, let's imagine what this is. This is a subspace, so it contains 0. How many dimensions is our subspace? It's a 3-dimensional space that lives in R4. It's a 3-dimensional space that passes through the origin in R4. And because this is in R4, you can't picture it, right? Just like a 2-dimensional plane that passes through 0, 0, 0 in R3, 1 dimension up, we have a 3-dimensional space that passes through 0, 0, 0, 0 in R4. So this is the row space. This is a basis for the row space. So the row space is equal to this, the span of this, and these 3 vectors form a basis for the row space of matrix A in R4. Okay? So how many dimensions is the row space? The row space lives in R4, but it's only 3-dimensional because there's 3 vectors. And this is a theorem that technically wasn't stated yet, and we're kind of, I've been saying it over and over. However many linearly independent vectors you have, that's going to be the dimension of your subspace. So row space is 3D. So it's a three-dimensional object, which is really a three-dimensional space that lives in R4. Okay. Now if we take a look at the column, use the column vectors of A that corresponds to columns of R containing the leading ones in the pivot columns to form the basis for column A. Well, first of all, where should we expect the column space of A to be? The column space of A would be in R3. So to get our basis for the column space, basically what they said here is to take all the columns that have those leading coefficients for each of the rows. So my basis for the column space is simply our standard basis.
True, but it's only sort of accidentally true. You have to go back to A in general, right? You can't pick out the things that are.
Oh, yeah, you can. No, I think you can do this because
Row reduction changes the column space, right? It doesn't change the row space, so you can pick the row space out of either one. But since it changes the column space, you can't take the column space out of R.
Right, yeah, I see what you're saying, so you can
Oh.
take it out of the original.
For example, R could have a 0 row in it, but that wouldn't necessarily
okay, yeah,
limit your column space.
Okay.
Unnecessarily.
yes, thank you. All right, so what happened? I don't know.
You have to choose vectors 1, 2, 3 from A.
So from the original A. So these are the vectors that have the leading ones. And so those very same columns in the original matrix, or yeah, the original matrix.
We still identify with the row reduced one.
You use the row reduced one to identify which columns to get, and then you get it from your original matrix. No, the row space doesn't change because it's a row reducing. So the row space for the original matrix is the same as the row space for if it's row equivalent. Right. So this is in R3, which is, we have three vectors that's supposed to be a basis for a subspace of R3. This forms a basis for the column space. And each of these vectors is three-dimensional, so we're living in R3, which we would have gotten over here anyways when we take a look at the number of rows. So what can you say about this particular subspace? Like how would this subspace look like? It's either, we're in R3, so it's either a line, it's either 0, a line going through the origin in R3, a plane going through the origin in R3, or all of R3. In this case, since we have 3 vectors, this is 3D, this is going to be all of R3.
What did this row of A, what did that span?
That spanned a 3-dimensional space in R4, going through the origin. So let's make it a little bit clearer here. A 3D space that it has the origin in R4. Okay? All right, any questions so far? Yes?
I'm a little confused. Where did the numbers for the span of row A come from again?
Span of row A. The span of row A. Oh, we went back to the original matrix A. Well, first of all, this is a reduced row echelon. And I look at column 1, column 2, and column 4 that have the leading ones for the rows. And then I take those same columns, column 1, column 2, and column 4 from the original matrix, and that's where those come from. C1 from A, C2 from A, C3 from A.
Okay. I asked about the rows.
Oh, the rows?
Yeah.
It's just these very same rows, except I wrote it.
Okay.
Okay. Yeah.
I got 2.
Oh, I'm sorry. One more, Miranda. I actually could have taken the rows from the original matrix since it was all of them. So I chose these rows because they were simplified, but I could have said 1, 1, 0, 1, 1, 0, negative 1, 1. I could have gotten the original rows from the original matrix, and it would be the same thing.
Okay.
But this is a little bit simplified because there's more zeros in it, so it's technically a nicer basis. Sorry, Justin.
That's all right. So the theory is telling us that columns that will row reduce to a single one will be, I guess, linearly independent. Is that the idea?
The rows that would row reduce, or
Yes, I mean, we get the REF and columns 1, 2, and 4 have only a, what would you call it? Only a 1.
only one, yeah.
Okay.
Yeah.
So those are the rows in the original
Those
matrix.
are the columns,
Those are the columns in the original matrix which are linearly independent.
which are linearly independent, yes, and that would make up your span.
Okay. And then my second question is, how do you go about entering this into the web assembly? Like when it wants a basis, it's like 4 blocks, and there's no way to enter like a vector.
It does want them to do like column vectors for the column space and row vectors for the row space.
We can change the size of it.
Yeah. So like you
Oh,
click on the arrows.
okay.
That's what the arrows do.
Yeah, and so if it makes a new graph, then that's because it wants column vectors. It's really weird.
So there's some actual dragging and.
Yeah, there's manipulation involved.
Good to know.
This would be 3.6 or 3.7.
3, 5.
Five, which basically all this extension on top.
Oh.
We haven't talked about the last two problems.
Like, what are these arrows? Would you say?
3.5. So I suppose I should extend that.
Could make some kind of rule where homework's not due until like a week after we've talked about it.
I would do it. I would just like not have that freak out even on Sunday night. You know, like, I'd be able to
Well, I think the whole idea behind the homework is to get you prepared for the test. And if I made the homework due right before the test, then you wouldn't be studying for the test because you'd be doing the homework and
I
stuff.
just do the homework simply because I don't understand what's going on in the talk. So that's why I do the homework though.
All right. Anyways, let's go back to this since we're out of time. Now the last bit. So the three things that we can get out of a matrix is the row space, the column space, and then the null space. So solve the leading variable Rx is equal to 0 in terms of the free variables, and set the free variables equal to a parameter substitute and all that stuff. So let's see. This is our R. Our R. 1, 0, 1, 0, 0, 1, minus 1, 0, 0, 0, 0, 1. That's our R. And if we write this equation, Rx is equal to 0, we are really solving for this system that looks like this. Now, before I fill it out, how many elements should I have in this x vector? 3 or 4? x1, x2, x3. Is that enough? No, because when we do the row times that vector, we need 4 things to multiply, okay? So we need x4. So the null space is in what dimension? The null space is in R4. Becca?
I was going to say, can we just do an augmented matrix?
We could, but if we do, then we would row reduce and then we'd get to the same spot. So we already did that work, and all we're doing is we're back solving. So my 0 is a 0 vector. Clearly, it should be a 0 vector. Where is my 0 vector going to live? R3 or R4? R3. And we can get that by the size of the matrix. Now, if we back solve, we see x4 is equal to 0. But now we have a free parameter here, right, for x3. So let's let that equal to t. How do we decide that's free? I don't know.
I guess I'm just seeing 3 rows and 4 x's, and I'm not sure how you make the decision.
Okay, well, if we
R3 is the fourth, like, axis is there, right?
what? What? Well, if we multiply this out, we're going to get x1 plus x2 is 0 and x3 plus x4 times 0 is equal to 0. We got 0 times x1, x2 minus x3 plus 0 times x4 is equal to 0. And then our last one is going to be x4 is equal to 0. That's by doing the multiplication. And so we have x4 is equal to 0. And if we start moving up to back solve, we have a free variable in x3. So we're going to let x3 equal to t, our free variable. And so x2 would become positive x3, which is t. And then our x1 is going to be negative x3, or negative t. So our null space is going to be, or can be described by x1, x2, x3, x4. It's a vector in 4 dimensions such that this is equal to t times coefficients of t, -1, times t is x1, +1 times t is x2, +1 times t is x3, and 0 times t. So now I have a basis vector, and so this is really saying it's the span of this vector. Right? If you take this vector, the span of this vector is going to be the null space. Yeah. Oh, the span. Okay, so how many dimensions is the nullity, or is the null space? It's a what? It's a one-dimensional space. It's a line in what dimension? 4 dimensions. Right? We're in R4 here. So it's a one-dimensional line that passes through the origin in R4. Again, we can't visualize it because it's in R4. Even though we know what lines look like, and we can imagine that a line would look like a line, even in a dimension that we can't figure, but you can't really figure that out.
You have a line in 3D that changes with time, it passes through the origin at time equals 0 to something similar.
You could think about it that way.
It's not quite 4 dimensional.
No. Yeah, I mean, if you're one of those physics people who thinks the 4th dimension is time, you can imagine. What? Wait, what? I'm not knocking them. They're just. If you're one of those people, then you can think about time as the 4th dimension, and at time 0, this is what it looks like. At time 1, it'll look something different.
What if it was like the the one we did at the beginning?
Well, could be a 0 for your test. I don't know. All right. We're wasting time again. Speaking of time. All right, so these vectors form a basis for the null space. So we got the null space. Okay. However many free variables you have in this system, then that's your dimension. That's all one vector.
So the null space is the line?
In this problem, the null space is that line. So everything on that line in 4 dimensions is going to make this matrix go to 0.
So you can describe a line as a span.
A span of one vector. One vector.
I thought it was linear multiples of.
Then it wouldn't be a line.
Right, but like you could have like.
Oh, you can
2 times that.
you can describe it. You can describe the span as t times that, a variable times that, times the one vector, yeah. Because if you have 2 vectors, then it would be a plane.
Right.
Okay? All right, let's move on. Here are a bunch of theorems and definitions that we've already been using, kind of abusing. S is a subspace, then any two bases of S have the same number of vectors. That leads to the definition of the dimension. The dimension of a subspace is going to be the number of linearly independent vectors. So linearly, a basis is understood to be linearly independent. So instead of saying basis, you can say the number of linearly independent vectors that span your subspace is going to be your dimension, which we've already been using that idea. Now here's a new thing, and based on the example that we had, if you remember, the row space had three linearly independent vectors. Our basis had three vectors. Our column space had three vectors. Now, even though those vectors live in R4 and R3 in different spaces, right, they still had the same number of bases. And so that becomes, for us, an important fact. And the fact is that the row space and the column space have the same dimension. Even if you don't have a square matrix, which we didn't over here, we had a 3 by 4 matrix. We found that the column space had 3 dimensions and the row space was 3 dimensions. And that's not a coincidence. It turns out that the row space and column space will always have the same dimensions, regardless of the size of your matrix. Okay? So since they have the same dimension, then you don't want to favor one over the other, saying, oh, I'll just say the dimension of the column space or the dimension of the row space. We'll just call it one word. And the one word that describes the dimension of the row space or the dimension of the column space is called rank. So the rank of a matrix is the dimension of its row space. It should be or, I suppose, huh? Or the rank is the dimension of its column space. Okay?
When you're trying to find the rank of the matrix, is it better to find the column, like is it faster to find the column space or row space?
Well, if you're trying to find the rank of the matrix, what do you think is better, to find the row space or the column space? Row space? For this one it is. When would it be good to find the column space? If you had, so whatever you have fewer of, if you have fewer rows or fewer columns, and then this next theorem actually gives us even more of an insight. So this one, we already talked about this matrix. We did the same matrix example in the previous page, so let's just briefly apply what we're talking about here. So we know that the dimension of the column space is equal to 3. The dimension of the row space is equal to 3. And that is exactly what the rank is. Okay? And in this next theorem, there should have been more space here, but in this next theorem, if we take the transpose of this A matrix that we got, so 1, 0, 0, 1, 1, 1, 0, minus 1, minus 1, 1, 1, minus 1. If we take the transpose of this, this will have the same results. the column space would still be 3, the row space would still be 3, and therefore the rank is equal to 3. Okay? Because they have the same rank. And we won't prove it, but if we just think about it and imagine row reducing this, we should get, you guys can figure it out. Okay. There's one more page of theorems and definitions. The last thing we're going to talk about in this section is the nullity, which is the dimension of the null space. And so this is like just being really meticulous with your notation. When you say the null of A, this is a subspace. When you say the nullity of A, this is a number, which is the dimension of the null of A. Okay? So there's this thing called the rank theorem, where it just adds the rank and the nullity, basically the row space and the nullity of a matrix. It says that a matrix A, m by n matrix, the rank of A plus the nullity of A should equal to n. That's the number of columns, right? So this is a 3 by 4 matrix. So your m is 3, your n, the number of columns, is 4. The rank is 3, the nullity. Remember that it had one vector in the null space, and so this should equal to n, which in this case is 4. Now remember that this is not a proof, this is an example, and we're applying this theorem to the example that we had. But that just confirms our ideas. Okay, questions?
Can we go over the fundamentals of invertible?
Okay, well, I don't know what you mean by going over it, but I'll
What is it?
put it in my notes, but I won't talk much about it. So, the fundamental theorem of invertible matrices started off, apparently we had something like this earlier on, but we only had A through E because we didn't know anything else. We didn't know about the rank, the nullity, and all that stuff. So what this is saying, let's just go through the list here. If A is invertible, then your inverse exists, right? And if your A inverse exists, it turns out that there's a whole slew of things that follow after that that's beneficial to us. That means that AX plus B has a unique solution. That means there won't be any free variables or any of that business. You can always find one unique solution. Okay? That makes sense because A inverse exists. So B is actually equal to, wait, X. X is equal to A inverse applied to B. So that's your unique solution. let's go to D over here. If it's invertible, then this whole thing will reduce down to the identity matrix if you do a reduced row echelon all the way. So that means if you reduce to an identity matrix and then you augment it with a 0 vector, then your solution's all going to be 0. So your x vector is equal to 0. So that's what C is saying. Okay? Because the inverse exists, you can reduce it to 1s in the diagonals, and then your augmented matrix with a 0 vector is going to be just 0. That's what it means to be the trivial solution. A is a product of elementary matrices. You can start with identity and just a bunch of row reducing, and even row swaps would give you your matrix A. Yeah?
Only, then B is sort of like not right, but because like, isn't the 0 vector part of Rn?
It is, but this is for the equation AX is equal to 0. This is the equation AX is equal to B.
Yeah, so if B is 0.
Then your unique solution is 0.
Yeah.
The 0, and then that's it. You don't have any other solutions.
Yeah, but it should say every B but 0.
It also works for if B was equal to 0. Yeah, because if B was equal to 0, your one unique solution is X is equal to 0. Okay, rank is equal to n, because we row reduced it to the identity, and then you have n of those vectors. So whether you look at the column or the rows, there's going to be n. This is a square matrix. The nullity is equal to 0 because you reduced it. You don't have any non-zero. You don't have any 0 rows. And the nullity is equal, since this is your only solution to the homogeneous matrix, then homogeneous system, then there's no one vector that's going to span it. It's just going to be the 0 vector. Okay? And all the rest follows from all the stuff that we were just talking about. The column and the column vectors are linearly independent. They span all of Rn because you've completely reduced it and you got 1s, 0s, 1s, and so they span all of Rn. And all the vectors in the row and column are all linearly independent. Okay? So that's the big theorem. It goes through, I guess there's 11 equivalences here. And we can add more. You know, the inverse of A exists could be added onto this because it's not explicitly said. I guess saying A is invertible means that exact same thing. But we can add a few more things. And this can kind of, I think there's a couple more that they're going to end up adding here after we take a look at more transformations in the next section. Justin?
Is the n in Rn now the same n as in n by n?
Yes.
Okay.
And so these are the same now because it's a square matrix. So there's no more m's here because it's all the same. It'll just be n. And that's exactly the same as that, yes. No, because, I mean, before we take a look at m by n matrices, but if we apply all these things to a square matrix, n by n, we find out that that square matrix is invertible, then all these things follow.
So it's not true for all
Yeah, if it's not invertible, then these things don't all follow.
In the case of like a 3 by 4, would we be talking about anything?
Well, we can still talk about spans. We could talk about these other theorems.
The R, would R4 be a meaningful thing?
Well, yeah.
Like a 3 by 4.
Yes, which is what we did earlier. You know, these things all live in R3 or R4, and so that is still meaningful to us if it's not square. but it won't satisfy everything in this list. Okay? All right. Are we good? All right. Whether we're good or not, we're going to move on. There's a couple more pieces of information here. And I guess I'll mention it, talk a little bit about it. So the fundamental theorem of invertible matrices apply to square matrices. Now let's go back and talking about matrices that aren't necessarily square. There's a couple of other important pieces of information that we should try to remember. The rank of a product of the transpose times A is going to be the same as the rank of A. That's a bit of a surprise, but if we take a close look at what this might look like, we'll see that the product of a transpose and a matrix itself is going to end up being a square matrix. And then now, because it's a square matrix, then those other things could follow. The next order of business talks about more about subspaces and basis. Theorem 3.29 says that a subspace of Rn with k vectors, v1, v2, all the way up to vk, if that's the basis for a subspace, then any other vector in that subspace can be written as a linear combination of these vectors. Now that's one of those ideas that we kind of talked about already in detail. So in an example, let's take a look at R3. And then let's say we had two vectors u and v in R3. So they form a basis of a subspace. And how does that subspace look like? It's going to be a plane passing through the origin, right? Because it's a two-dimensional thing in R3. It's a plane passing through the origin. Now, if I pick any other point on that plane, that point can be written as a linear combination of u and v. Like if we scale u and we scale v and then add them together, we can get to that point as long as it's on the plane. If the point is not on the plane, then there's no way we can use the same two vectors u and v to get to that point that's not on the plane. Is that idea okay? Does that idea make sense? That's what this is saying. Every point on the subspace can be written as a linear combination of the basis vectors. Now, this last bit of information here tells us that we can write a coordinate vector with respect to a basis vector. Now, we've been using coordinate vectors with respect to a particular basis vectors for a long time, right? So for this one, let's take an example in R2. Okay, let's take a look at, let's see if I can write it. Let's write a basis vector in R2, a set of basis vectors in R2. And the easiest and simplest and basis vector that we know of is like, what is it? 1, 0, and 0, 1. Right? Now, in R2, if we look at a point, let's take a look at the point 2, 2. Well, just by me saying the point 2, 2 says that we can get to that point with this vector (1, 0, and 0, 1) by extending one of those vectors by a length of 2 and then extending the other vector by a length of 2 and getting to that very point. So what I'm saying here is that if I take my first vector and multiply this by 2 and take my second vector and multiply that by 2, then I'm going to get to 2, 2. So my coordinate vector with respect to this basis is 2, 2. Or vector 2, 2, depends on how you want to write it. I suppose they write it as a column vector. And that seems kind of ridiculous. Why does that even matter? Well, why that matters is that because if for some reason you come up with another basis that's not the same as your standard normal basis vectors, then we can write the coordinate vector with respect to a different set of bases. So let's pick another basis. So give me two linearly independent vectors in R2. Then that would form a basis, right? Because it's two vectors, it's linearly independent, it's in R2. So should I pick one or should you pick one? Oh, I was afraid you're going to pick something. 5, 0. 5, 1. Boy. Okay, whatever. Let's see. Well, nothing. I was trying to make my life easier, but it's okay. So, if this is going to be my new basis vectors, now these vectors are linearly independent. We agree on that? And there's two of them in R2, so they have to span all of R2. Which means I can get to any point in R2, which means if I have the point 2, 2, I should be able to find a constant times the first vector plus another constant times the second vector. Can somebody find this real quick? Because we got a hard basis vectors that Becca gave us. Oh, there's a 0 there, so this has to be a 2. Okay. So now let's figure out how to make this 5 become a 2. So 10 8/5 minus 10 minus 8/5 is going to give me 2. Is that good? All right. So now, if I change my basis vectors, I have a new coordinate vector. So instead of saying 2, 2 like I did with the nice standard basis vectors like we've had, my new vector is going to be written as, so this is a coordinate vector with respect to, WRT with respect to, the second basis vectors that we got. And that's going to be written as, now, the order is going to be important for the basis vector, so we would write the order accordingly. So it's going to be negative 8/5 2. Because that's the first vector that we chose to be first, and so this number here, it's a scalar multiple. So since we chose this to be V1, then this has to be your C1. If we switch the order, then your order is going to be switched. What? WRT with respect to?
Like the coordinate vector is like written as like the V sub 3 whatever.
Yeah, so this is your vector V, negative 8/5 comma 2, sub B, and this is the basis vectors that you're talking about. All right? So depending on your basis vectors, your coordinate vector, or how you're going to write your vector, is going to change. And it would be really, really nice if we had our standard coordinate vectors. But sometimes we don't have that luxury. We are stuck with a different basis. And so we're going to have to rewrite our coordinates a little bit differently.
But they don't those, like, don't they have the same span? So like, why does it matter?
Well, it doesn't matter because you can write your basis vectors like this.
Right.
But what if you're in a plane? How is your basis vectors going to look like? Where there's a lot of neat ways to write your basis vectors. So you're going to have to choose one, and then whatever one you choose, you're going to have to use that as your basis that you're going to want to use.
And then what do you do with that?
Where you can write the coordinate vector based on those bases.
But like, no, I mean, but like, what do you do with the coordinate vector?
Well, if you're on this plane and you want to get to another point, you have to use these vectors as the basis to get to any point on this plane. And so instead of writing these vectors all the time, you can just say, okay, how many times did I multiply, how much did I multiply u by, and how much did I multiply v by to get there? And then you just use those coordinates, those scalars.
I think it's just to show if you pick any two linearly independent vectors, you can multiply it by a coordinate vector and get any other vector in its subspace, right?
Yes, kind of.
You're multiplying the vector.
You're not multiplying, you're taking these numbers as the coefficients of the linear combination of those vectors.
So it's sort of like you're multiplying.
Yeah, it's sort of like you're multiplying.
vectors are actually now like coefficients of
Your vector is now made of the coefficients of those basis vectors, yes. That's a good way to put it.
Why would you pick the vector?
Well, like I said, if you're living on this plane, and then all you have to go by are these basis vectors over here, and you want to get to another point on this plane, so instead,
I get that. It's just like, why are we putting it in? Like, why are we putting scalars in?
well, because you have no more reference. If you're on this plane and you're in R3 and you don't know where the origin is in R3, you're going to create your own origin. I guess you have to know where the origin is, but you're going to create your own origin on the plane, and then you're going to use these vectors to move around to get to a point. Now, how are you going to get to this point? Well, instead of expressing this point as something in R3, since you live in R2 in the plane, not in R2, but in the plane, a two-dimensional plane, you only want the two vectors that will get you there. And the two vectors that will get you there is a linear combination of this vector and this vector, and that will get you to that point. Well, the only information you need now is how much did you scale this vector by and how much did you scale this vector by. And those are the only two pieces of information that you need. And you make a vector out of that, and then now you have...
Used for storing the scalar.
Yeah, one way to look at it. Okay? Is that... Is that okay?
Not okay.
Not okay.
All right.
Yeah, all right. It's all about the base. I've been waiting so long. It's all about the base, Basis vectors, that is. The test for this class isn't soon enough.
It's November 11th?
Yeah, the test is supposed to cover chapters 3 and 4, but we're just kind of sailing on chapter 3. So we're going to talk a little bit about chapter 4 right before the test, but we're... What? What's so funny?
Like if you put up like an HDA or if like you decided it's going to be a test or something.
All right. Here's the deal. This is what we're struggling on today. Talking about today. We're going to talk about linear transformations the last 5 minutes, and we'll do more linear transformations and applications on Wednesday. On Monday, we'll finish off the chapter with the applications, and then we'll start talking about eigenvalues and eigenvectors, which is in chapter 4. And then we'll also do a review next week on Wednesday. And then we have a holiday. Yay. And then we have a test. Good news and bad news.
What day is the holiday? Is it Monday?
The holiday is Monday, November 10th, and the test is on Wednesday. Yeah, it is right here. So that's our schedule, which means we're going to barely get into chapter 4, just introducing eigenvalues and eigenvectors. But I think it's an appropriate introduction because one of the applications we're going to talk about at the end of chapter 3 is like the beginning of the idea of eigenvalues and eigenvectors. I don't know. We're not there yet. I'm not going to talk about it. So that's the end of this section, finally. And our next section is Introduction to Linear Transformations. So just to have something in our notes for today about linear transformations. Linear transformations are like functions, except instead of taking, you know how functions are, right? Functions. You learned that in pre-calculus or whatever. So we have y is equal to f of x, or f of x is equal to x squared. You take a number and you do something to that number and you get an output. Input, output business. Okay. Transformation is the same thing, except instead of just taking a number like 3 and then squaring it and getting 9, instead of just taking a number, you're going to take a vector. Or you can even take something weird like a function. You can take a whole function, like the sine function, and pass it through a transformation machine and get something out of it. Say I had a function like x squared, and I pass it through this transformation machine, and I get 2x. And then I get another function like sine x, and I pass it through the transformation machine, I get a cosine x. And I take another function like How am I transforming my inputs and outputs? The derivative. So I have x squared, transformation machine, my output is a 2x, right? So that is essentially a function. You're passing something through it and you're getting an output. So the transformation is the same thing, except instead of just numbers, you can transform functions, you can transform vectors, transform matrices, you can transform whatever else you want. So what we're going to be doing is a transformation of vectors. We're going to take a vector, we're going to pass it through a transformation machine, and we're going to get an output. And what we're going to try to do is describe this transformation with, instead of functions, we're going to describe it with, if it's a linear transformation, we're going to be able to describe it with matrices. So a transformation is a mapping or a function going from one space to another. This, we're specializing now. We're not doing transformations in general. We're talking about a mapping from Rn to Rm that takes a vector and then gives you another vector in a different space. Or maybe in the same space, right? Like shifts or rotations or things like that. We'll talk about what transformations are considered linear and what transformations are considered nonlinear. And we'll get to talk about that. Okay? So that's going to be our topic of discussion for next time, transformations. Or linear transformations. All right. I'm going to put an HBA up. I forgot to put it up last week. And I'll put an HBA up. It's not his fault.
It's not his fault.
No. It'll be due after the test. I'll give you a little bit of time.